Hi everybody, Eric here. Going to do a quick discussion on dipole moment. This is a common problem that I think isn't always very clear to students. So I'm just going to go over some of the topics real quick. I've got three equations that I'm going to go through, and I'm going to explain what a dipole moment is. All right, so dipole moment is so if you have two charges of the same magnitude separated by some distance, the vector from the negative charge that points towards the positive charge is your dipole moment. So I'll explain that again. Your dipole moment is represented by the letter P, and it's going to be equal to the magnitude of your charges, so Q, the distance between the charges, L, multiplied together. And then the direction of your dipole moment, since it's a vector, is going to point from your negative towards your positive. So it should look like this. All right. So don't get that mixed up with the electric field vector, because the electric field vector points from the positive to the negative. Dipole moment is not the same. So that's your dipole moment, the vector here. The distance from here to here is what we're calling L, and then Q is the magnitude of these charges. The important thing about these charges is that they have to have equal magnitude. So if this charge is 3 coulombs, this charge will be negative 3 coulombs. If this charge is negative 22 coulombs, this charge will be 22 coulombs. And then the number we plug into our Q is just going to be the magnitude of a single charge. We're not going to add them or anything. So again, if this is 3 and this is 3, the number we plug into our equation is going to be 3. And then L is going to be our distance. And that's how you calculate the dipole moment. Now, a usual question presents a dipole that is in an electric field. So let's say we have an electric field, E, perpendicular to our dipole moment. So it's in this direction. So our dipole is sitting in an electric field. And this is a uniform electric field, even if my spaces don't look even. Now, what's going to happen is that since an electron is in an electric field, we can remember that our equation for an electron or any charged particle in an electric field is F equals the charge of our electron or particle times the strength of our electric field. So this particle in an electric field is going to feel a force, which is what this equation states. And the direction of the force on the positive charge is going to be along the direction of our electric field. So this thing's going to feel a force up. Let's make the force that this thing feels up, right? And the negative charge is going to feel the force opposite of our electric field. So this is going to feel a force down. And what we're going to get here is a rotation, because this is going to want to move up, this is going to want to move down, and it's going to be a rotation. And whenever you have force separated by some length, you get what's called a torque. So that's how your torque equation relates to your dipole. So the equation for that is going to be torque is equal to the dipole moment that you've calculated cross product with the electric field. So this relationship is a cross product. So I'm not going to go through the vector version of cross products. So if a question on how to do the vector version of a cross product, please ask. But the magnitude version of a cross product looks something like this. Torque is equal to P cross E, which is what I have already. But that's going to be the same as saying the magnitude of our dipole moment multiplied by the magnitude of our electric field multiplied by sine of theta. So we use sine here because it's a cross product. There's what's going to happen is the theta is going to be the angle between the electric field and our dipole moment. In this case, it's 90 degrees. So sine of 90 is 1. So our torque on our dipole here is just going to be our dipole moment times our electric field. And it's just going to give us the number there. Cool. Last thing I wanted to talk about is once you've calculated the torque, how do you calculate the potential energy? So potential energy, U, is a scalar quantity, which means that I'm going to get a singular number from multiplying two vectors. So my dipole moment is a vector, and this time it's going to be a dot product. So I'm representing the dot product by this star, but it's going to be a dot. So dot E. And if we remember, I talked about this in my last video where I referenced dot product. But the potential energy here, in this case, is going to also be equal to P, the magnitude of P, the magnitude of E, cosine theta. So our potential energy in this case that we have set up, we're going to plug in 90 degrees for theta. Cosine of 90 degrees is 0. So our potential energy here is 0 in this setup when the electric field is perpendicular. Cool. So that's just a quick rundown of dipole moments and how usually the 3 questions you'll be asked when determining the dipole moment. So hope that helped a little. If not, feel free to send me an email, ask a question. But this is just a quick discussion. And you guys stay safe out there. Virus is still happening, so stay indoors and study some physics. All right, see ya.